graph. I guess you don't have to look at a graph either. Okay, so after you check all those lovely conditions, we can do a significance test for capital B, beta, and we want to know, we're going to test the hypothesis. Capital B equals B null. This is the null. It's what we assume it to be, and typically, I would write this down, you guys, we assume 0 with the slope. In other words, there's no relationship. There's no positive relationship. There's no negative relationship. That would be the assumption. We're checking, is there a positive relationship for the slope, or is there a negative relationship with the slope? So our test statistic is T. Just a reminder that this is the formula that's on your sheet for every single one of these, whatever we call these, our test statistic, okay? So our test statistic in this case is T. It's the statistic, which in this case is little b, minus the parameter, which is b null, which is typically 0, divided by the standard deviation of the statistic, which is the SEB that you can get from your calculator, or some of you can't, so we'll have to figure that out, how you're going to plug that in. You'll just put it, I guess, SEB, and then you'll get it from the test. All right, so find the p-value by calculating the probability of getting a test statistic this large or larger in the specified direction. All right, so for an alternate hypothesis, this is kind of hard to read, that's HA. Typically, if it's this guy, we're looking for greater than 0 means, is there a positive relationship? So our alternate hypothesis would be, on that one, a positive relationship. This one would be that there is a negative relationship between the two. And the last one, we have the two-sided. If we're not sure, then you say not equal to 0. Basically, there's some sort of relationship, but we don't know which direction, okay? Degrees of freedom is still, n minus 2. Don't know what's happening. Sorry, guys. Wow. Oh, no. I'm staying attached to things. It's not good. Okay. I hate when my computer does this. All right, you guys, we'll see if we can do this. So, significance test. Let's run through one. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Crying more means you might be smarter. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. Not mean at all. The researchers recorded the crying and measured its intensity. Child abuse for you guys? All right. Of the peaks in the most active 20 seconds. They later measured the child's IQ at age 3 using the Stanford Binet IQ test. The table below contains data from a sample of 38 infants. I know. All right, so they give us the output. We've got our normal scatter plot first. We've got all the information, regression analysis, which you guys need to be able to read what is what, those important numbers. So this guy right here, what's this one? Alpha. Okay, that goes in for our y-intercept. What's this one? B. This is our slope for our regression line. Okay, and what's this number? Because this one's special too. SEB. Okay, that's SEB. And then we only need these two right here. They actually give us the t value and the p-value. All right, our test statistic is given and our p-value is given. I still want you to plug in for the formula. All right, and then we've got our residual plot right here and our normal probability plot of the residuals, which looks fairly linear when we check everything, okay? All right, what is the equation of the least squares regression line for predicting IQ at age 3 from the number of crying peaks or the cry count? Interpret the slope and y-intercept. All right, so you get those values from that lovely output they give us. So the predicted IQ score is equal to alpha, that's your y-intercept, right? Plus 1.4929 times the cry count. So where are those two numbers? Right here and right here. 91 and 1.49. Okay, we got to interpret both. So the slope for each additional crying peak in the most active 20 seconds, the regression line predicts an increase of about 1.5 IQ points. So for every increase in whatever the x variable is, you guys remember that? The y either increases or decreases by whatever the slope is. All right. And the y-intercept, the model predicts that an infant who doesn't cry when flicked with a rubber band will have a later IQ score of about 91. So the infants who don't cry have lower IQ scores, according to this study. Don't know. Do you always have to, like, interpret it? Only if it says. All right, explain what the value of S means. My board isn't working, you guys, so I kind of have to be over here. So explain what the value of S means in the setting. So you guys have to look at this right here. Here is S. Anybody remember what S means? Standard deviation, typical distance from the regression line. Okay, S is the typical distance from the regression line. So the size of a typical prediction error when using the regression line in part A is 17.5 IQ points. That's your S. Okay. Do the data provide convincing evidence of a positive linear relationship between crying counts and IQ score? So notice, you guys, it says of a positive relationship. So what am I going to do for my alternate hypothesis? Greater than 0. Okay? So our null hypothesis is that it's 0. That means no relationship between the variables. Some of you guys aren't even looking up here, and that kind of scares me. The alternate hypothesis is greater than 0. So we want to perform a test of these two things here, and you have to define B. So make sure in your state you define what B is. B is the slope of the population regression line relating cry count to IQR. All right, so it's population or true regression line, the slope, right? Relating those variables, and we're using confidence level of 5% since they don't tell us, or a significance level. Okay, plan, you might want to write this down, the name of the test. Write that down, t-test for slope. And let's go through liner. So we'll put these lovely graphs up here and see if we can do it. David S., what's the L stand for? And do we have linear? Y. Okay, and our residual plot has no leftover pattern. This actually tells us normality. All right, so for linear, I would use this one. No leftover pattern, okay? Okay. All right, and Chelsea, what's the I stand for? Independent. So do we have independence on this one? Why? On this one, we actually want to check 10%. So there was 38. So there's probably 380 babies. So we're probably good to go. Okay. So check your 10% rule. There's at least 380 infants in the population. All right, and N, Abby, what's N stand for? And do we have normal? Yes, and I would look here. And so you need to say that the normal probability plot of the residuals is roughly linear, okay? And then we've got no strong skew or outliers also. So E, Jake, what's E stand for? And do we have equal standard deviations? Which graph? The residuals. You want to use this one. Residuals, these are about equal distance all the way across from left to right. Okay. And random, of course, we have 38 infants were randomly selected. Okay, so what you need to show for the do part is this guy right here. So there's your t equals b minus b null over SEB. I want to see the numbers that you plugged in. Where did we get this b from? The slope from Minitab, okay? That 1.4929 minus 0 over SEB, not S. So where do I get the 0.487 from? That would be right here, SEB, 0.487, okay? Everybody got that? And plug it into your t value, you get 3.07. And then our p value, you guys, we can actually use our calculators, of course. So I'm going to show you how to do this. So you plug them into lists, right? You guys remember plugging into lists? Yes, but if they don't, right? Because this one does, but sometimes they don't. If they don't, go to menu, statistics. What do you think we go to? Yeah, we're doing tests on this one, not confidence intervals. And you want linear regression t-test. Linear regression t-test, okay? Then you got to put your lists in. So cry count was the X list, IQ is the Y, and you have to do your hypothesis. So on this one, we're looking for the relationship being positive, so greater than 0. And we've got our T, our p-value, our degrees of freedom, SEB, okay, everything we need basically in that output. So our p-value, 0.004, and then degrees of freedom, make sure you always write that down. And then, of course, our conclusion. Because the p-value is less than alpha of 0.05, we reject the null. There's convincing evidence of a positive linear relationship between intensity of crying and IQ score in the population of infants. So there is a relationship that's positive, yes. All right, you guys, so based on the results of crying and IQ, should we probably like hit our babies with rubber bands so they'll be smarter? So you guys, this is back to chapter 3 where correlation does not mean causation, right? There's just correlation between the two. One thing doesn't cause the other thing. So when you're doing linear regression, yes, there's a positive relationship. That doesn't mean that doing this to your baby is going to make it smarter. I mean, you can try it, David, if you want to. There's how to do it on the TI Inspire, you guys. Don't forget. And your homework.